Hi everyone, my name is Vinay Mittal. I'm representing Group 10 of AAI590. Today we are representing Solar IQ, a system we built that uses artificial intelligence to automatically figure out how much money you could save on your electricity bill by putting solar panels on your roof. So before our project, answering this question which I just mentioned meant either hiring a specialist to come and visit your home or using a rough online tool that didn't really look at your virtual roof. So we wanted to change that by making the whole process automated, fast, and free. So just point uh, orthogonal image at your roof or maybe a satellite photo of your house, and our tool does the rest. Starting with our outline, here's what we're going to walk through you today. We'll be starting by explaining why this problem matters and why existing tools fall short. Then we'll show you the data, what we trained upon, how we cleaned it, prepared it, and which AI models we tried. We'll explain how we trained those models, essentially teaching the computer to recognize rooftops and photos, and then show you the actual numbers on how how well it worked. Right. Finally, we'll show you a live demo of the complete system, which takes satellite image and spits out the projected dollar savings estimates. We hosted that on our weakness, so yeah, maybe that can be seen separately. So right, let's start with the problem and motivation. See, think of a solar panels the way you think of buying a car. Before you commit, you need to know if it's worth it for your specific situation. The same problem is that figuring out your specific roof's solar potential today either costs hundreds of dollars for a site visit or relies on a tools like Google Sunroof that only work in certain cities and treat your roof as rough address. In our tool where we are actually measuring the surface. Talking about the EDA to teach our models to recognize the rooftops, we needed thousands of satellite photos where we someone already has labeled it. We call it as labeled data. So for that we used INRIA aerial image labeling dataset, which gives us 180 aerial photos across 5 cities, which you can see here: Austin, um, Kitsap. These are in US, Vienna, West Tyrol, in Austria. So each photo covering about 1.5 square kilometers at resolution detailed enough to see individual cars. The most important thing we found is that lattice building only covers about 17.6 pixel percent of the pixels. So yeah, the rest is road, trees, and grass. Talking about the pre-processing pipeline, we used see the raw satellite photos were used. So each one is having 5,000 by 5,000 pixels, which is too large to fit directly into our A model. So we cut each photo turn into 5 by 2, 512 by 512 pixel styles. This kind of saved us 50% of the memory, as well as cutting the large pieces into slices. We already make sure that the overlap is there. Where we see a rooftop, um, so the near the edges is more accurate. So this way the model sees every building from multiple perspectives during the training. We also had to normalize the color so that the bright sunny photos from Austin, cloudy photo from the VNR look comparable to AI, much like adjusting your camera's white balance. Now, during training, we also artificially varied the images, flipping them horizontally. We call them as image augmentation. And talking about the ML model, we tried three different models here. Think of these three different strategies for solving the same puzzle which we started with. The first is called a simple FCN. Here, FC instance for fully convolutional network, the most basic approach. It processes the images through various series of filters that gets progressively better at spotting pattern, then produces a pixel by pixel map of what it thinks building are. The second is UNET. It's more sophisticated design that we originally invented for medical imaging to outline tumors in scans. But later on it was more popular for segmentation, I believe. So yeah, this is what we used. It is two clever part. Structure one half compresses the image down to understand the big picture, and the other half zooms back while pulling in detail from the first half. This was our best performer. The third one was the mass RCNN. This is the most advanced one though, but this is not what we caught as the best one. So not talking too much around it. Now I would like to invite my partner in this group, Antan Tyagi, to continue on this presentation. Thank you very much.
Thank you, Vinay. Looking at training strategy and optimization. So for the training of the unit, we follow two-stage freeze and freeze procedure with a loss formulation and hyperparameter search. In the stage 1 to 5, our encoder is frozen, and only the decoder trains. This is because we want to prevent pre-trained ResNet 18 weights from being corrupted by large gradients, which is due to the data that we have right now. So the intersection over union values moves from 0.45 to 0.63, which is quite a good jump on the training path. The hyperparameter search space exploit our learning rate, class weight, encoder freeze based on number of epochs, and the loss function. The stage 2, which we go after epoch 6, is the full fine tuning. We train the entire all the weights, the learning, but we reduce the learning rate on plateauing. When our loss starts plateauing, we reduce the learning rate with a patient strain factor of 0.5. The best validation IOU based on that value was 0.7060. And for the second part, we combine a loss training function with a weighted binary cross entropy, and then the dice loss, which is there to directly optimizes the overlap and improves the F1 score. So looking at the model performance, we see that our unit ResNet 18 has the best IOU and F1 dice score, and it's the best model in production. Mask RCNN does not have a F1 dice score because it's an instant segmentation. So unit kind of performs better than mass RCNN despite being a simpler model, because dense Vienna building layout impacts segmentation and instant level proposal. But the semantic segmentation handle boundary ambiguity more gracefully, and hence the performance is better. If you look at the training and validation graph, they follow closely each other. In the stage 1, we do see a jump start from 0.39 to 0.62. Then after full fine tuning, we finally observe the IOU going to 0.7. Since the performance of the train and validation tracks closely, model is generalizing well from US cities to Australian validation city. And we trigger the learning scheduler at epochs 10 and 30, and then both of them produce IOU improvement. The end-to-end pipeline includes sending a satellite image patch, doing a unit segmentation with the rooftop area estimation and energy estimation. We get an annual savings. And you can find an example with a San Diego CA example. If a rooftop area with 270.8 meters square and the energy estimated and tariffs were derived from the APIs that we have listed, we get an annual saving of approximately 5,861, which is 50 meters square per install. And if we look at the solar potential of geographic variation, we see that 65% is a GHI spread is 65%, which is Phoenix has quite a high value compared to Seattle. Even with same roof, the yield is vastly different. California is kind of more attractive, and the combined impact of Phoenix plus high tariff is three times the dollar savings of Seattle. And equity dimension, if you based on the analysis, we look at low income areas are disproportionately located in high tariff state and should be flagged as a priority zones. The final outcome, which is a grade U app, is deployed on the Hugging Face. It's publicly zero. It doesn't require any installation. You just upload your rooftop and you can get an estimate. It has a full API integration with NASA Power, EIA, and Census ACS information to provide you a reliable estimate. Some edge cases for this we identified as large industrial roof, which are model over segments, plus rural areas in which the tiles data is quite sparse. The masks are a little bit noisy. And so what's the outcome of the project? What we find is unit is better than mask RCN and dense geographic settings. Two-stage training was critical, the freezing encoder prevent gradient corruption, and it can be used as any transferable pattern for any pre-trained encoder plus decoder combination. The limitation is resolution mismatch. Model is trained on 0.3 meter per pixel in RE tiles. Variable satellite image is slightly different from that, so we might have to tune those before moving into production. The energy model is a little bit simplified and does not capture the entire world dynamics, which if we want to do a more accurate prediction of it, we need to create a more simplified energy model. Future works in the project include building true instance segmentation instead of the semantic segmentation, near infrared channel, which helps us distinguish tree canopy from rooftop, which reduces our main false positive rate, 3D roof geometry, which is useful for pitch and orientation estimation and can help in differentiation of flat roofs, expanded training data across the world instead of the limited in RE district, and then building a production API and scale with a fast API service behind it distributed encoding, so that can work across geographies. So the key conclusion is unit IE was 0.7. Semantic turned out to be better than instance. We deployed an entire pipeline Hugging Face, and the impact is 65% GHI variation plus 3x tariff variation. And we identified solar economics, which are dramatically different based on location. Thank you.